Welcome to the lecture on land and technology. Technology has always played a transformative role in human interaction with land. From early surveying methods to today's cutting edge tools, technology has shaped how land is used, managed, and understood. In this lecture, we will explore the role of technology in land governance, focusing on key innovations, their benefits, challenges, and real world applications. By the end of this session, you will understand the relevance of technology in addressing global land management challenges, key technological advancements influencing land use and governance, the benefits and challenges of integrating technology into land related processes. What is technology? At its core, technology refers to the application of scientific knowledge for practical purposes. In the context of land governance, technology encompasses tools and systems that facilitate efficient land management, such as geographic information systems, drones, and blockchain technology. So, why should we use technology in the matters of land governance? Global challenges like population growth, urbanization, environmental degradation, and land conflicts demand innovative solutions. Traditional methods of land administration, often manual and fragmented, struggle to keep pace with these complexities. Technology offers scalable, transparent, and efficient systems to address these challenges and promote sustainable land use. Let's understand the role of technology by exploring the first one is dynamics of land information. Throughout this course, we have seen that relationship between humankind and the land is dynamic and constantly evolving. Land serves multiple roles in human life, from being a source of rights and livelihoods to a foundation of public administration and development. Each land parcel carries attributes that must be understood and managed for sustainable use. A single land parcel has both tangible and intangible attributes. Tangible attributes are the ones which include physical dimensions, soil fertility, vegetation cover, location, and others. Intangible ones include ownership rights, market values, zoning characteristics, cultural significance, and others. The interplay of these tangible and intangible attributes is critical to understanding true value and potential of land. As human interaction with land evolves, driven by urbanization, technological advancements, and environmental changes, the data associated with land must also evolve to remain relevant. As illustrated in this particular table, in pre industrialization times, social and political hierarchy was dependent on land ownership, and hence public records of data were primarily for fiscal purpose that the only focused on ownership and taxation. During the Industrial Revolution, land became a commodity, leading to establishment of land markets. Hence, the land records and cadastre, that is, parcel and up-to-date land information system containing a record of interest in land, focused to support land transfers and land market. As the time progressed, the need was felt for multidimensional records with data that integrates land use, environmental impact, population density, and real-time changes. Accounting for these attributes is crucial for managing land sustainably. Comprehensive land data is not static, it evolves alongside technological progress and changing human needs. The second aspect is, let's understand the relevance of technology in addressing pluralism. The relationship between humankind and land varies significantly across regions and evolves over time. Technology can help to adapt these dynamic relationships and account for diverse contexts, including urban areas where active land markets and informal settlements pose challenges requiring advanced tools for efficient land management. Second one, titled and untitled rural areas. Managing agricultural land, grazing lands, and rural settlements often necessitates tailored approaches. The third one is traditional or indigenous rights. Many areas have no formal markets but operate under traditional or communal land tenure systems, requiring sensitive and inclusive technological interventions. Fourth one, common property tenures. Shared resources like forests or water bodies demand innovative solutions for equitable governance. The fifth one is varied development stages. Countries and regions differ in their levels of development and land administration capacities, requiring scalable and context specific technological solutions. As situations and relationships with land evolve, the cadastral and technological responses proposed today may not be sufficient for tomorrow. Flexibility and forward looking designs are crucial to ensure that systems remain relevant in addressing emerging needs. Technological advancement developed tools that are driven by societal and administrative demands. These tools emphasize the scalability and the ability to transcend traditional institutions and methods. These tools have touched upon the aspects of land administration that coordinates land rights, continuum, and cadastral intelligence. It has also done impact on emergence of geospatial technologies. Hence, this tool in turn influenced cadastral systems in terms of information technology advances such as facilitating digital record keeping, analysis, and integration. It has also impacted communication technologies such as platforms like World Wide Web and wireless application protocols or WAP have revolutionized how land related information is accessed and shared. The next one is spatial information technologies. GIS technologies have transformed data management, manipulation, and integration. The other one is blockchain and cloud technologies, ensuring secure storage, retrieval, and safety of land records is done through these. Legislative and institutional reforms continue to support these technological advances, ensuring cadastral systems remain efficient and adaptable. Now let's explore some of the key technologies that are widely used and getting adopted in land management, such as remote sensing. This involves use of satellites and aircrafts to collect data about Earth's surface without physical contact. For example, satellite imagery helps us analyze vegetation, soil types, urban sprawl, and even disaster affected areas. Sensors on satellites or drones capture electromagnetic radiation, that is, the light or heat reflected or emitted from the Earth's surface. These signals are converted into images. The applications of remote sensing include urban planning. So, when we are thinking about urban planning, remote sensing is used to map cities, identify land use zones, and track urban expansion. They can be also used for land use mapping, which has helped in monitoring deforestation, desertification, agriculture pattern identification, and stuff like that. At a local level, it can help a city planner zone residential or commercial areas. At a global level, it tracks changes like melting glaciers, global deforestation trends. The second technology is GIS or Geographic Information Systems. GIS is a digital tool that integrates spatial data like maps with attribute data like population, soil type, and land ownership. It allows for advanced analysis and visualization of the data. The application of GIS includes overlay of different types of data, that is population density on transportation network or land use, to make informed decision. It allows prediction of urban growth and plan infrastructure accordingly. We can also manage resources by identifying areas with potential for agriculture or conservation. The third technology is use of drones for land surveying and precision agriculture. Traditional land surveys using total stations or GPS are time consuming. Drones provide an efficient alternative by capturing high resolution images and creating 3D models of the terrain. It facilitates faster and more accurate surveying and provide the ability to access hard to reach areas like mountains and wetlands. Drones can create detailed topographic maps to guide infrastructure projects like roads and buildings. Secondly, use of drones to facilitate precision agriculture is also very important. They are equipped with cameras or sensors that can measure crop health. That is, using multispectral imaging, we can understand how good health of the crops is. We can assess soil conditions by analyzing moisture level. We can look at pest infestation and nutrient deficiencies. Farmers can use this data to apply fertilizers or water wherever it is needed, reducing the waste. It can monitor large fields in less time, and it can boost crop yields by proactively doing certain steps. Then comes AI and big data for predictive modeling and resource management. AI, or artificial intelligence, it uses machine learning to analyze complex data sets and identify patterns which we might miss. Applications of AI include predictive modeling, that is, AI can forecast future urban growth, helping policymakers to proactively plan land use. Natural resource management includes AI applications such as analyze water and soil data to ensure sustainable use of these resources. AI is used in disaster risk assessment where prediction of floods, earthquakes, and landslides could be done. In terms of big data, it refers to massive amount of data collected from various sources such as sensors, satellites, social media, and weather systems. Applications of big data include tracking changes in land use land cover over time for analyzing satellite images and historical records. It also involves monitoring environmental conditions such as air and water quality in real time. And it allows optimizing urban infrastructure by studying transportation or energy consumption patterns. The next one is blockchain for transparency in land ownership records. So what is blockchain? Blockchain is a digital ledger that records transactions in a secure, decentralized, and tamper-proof way. Each transaction or a block is linked to the previous one, forming a chain. Once recorded, the data cannot be altered. Let's understand the applications of blockchain in land management. It can ensure that land ownership records cannot be tampered with or falsified. Land disputes often arise from unclear and forged ownership documents. Blockchain stores these records digitally with unique identifiers, reducing such disputes. Land records on a blockchain can be accessed by authorized stakeholders like government agencies or buyers, making the system more transparent and efficient. Automated processes using smart contracts can facilitate land sales. For example, once both buyer and seller fulfill their conditions, ownership is transferred automatically. Countries like Georgia and Sweden are already using blockchain for land registries, setting examples for others to follow. Now we will look at some of the examples or case studies to understand these applications further. The first one is adoption of technology in urban land management. Smart City Mission in India was launched by the Government of India in 2015 for the urban renewal and retrofitting using smart solutions. It was an initiative to establish a reliable model for urban development to adopt technological solutions in urban governance, infrastructure, and planning. As part of Smart City Mission, Pune Municipal Corporation launched Smart City Portal equipped with geographic information systems. It is a web portal used to find and access geographic information and associated geographic services on the internet. It supplies datasets, services, and applications to the city staff as well as to visitors to the website and other departmental sites. The portal is used to support decision making by providing real-time data on infrastructure, roads, and other areas. This is an example of GIS where GIS is integrated in smart city initiatives to provide spatial data to public as well as to fill the information gaps across the departments. The second application of technology is for agricultural lands. Let's understand what Digital Agriculture Mission of Government India is about. It is an umbrella scheme aimed at using technologies to improve farmers' lives. It has two key features. The first one is AgriStack. It is a farmer-centric digital public infrastructure to streamline delivery of services to farmers. It includes three components. A. Farmers Registry for issuing Farmers ID. B. Georeferenced village maps for linking the farmer ID to farmers. C. Crop sown registry for maintaining a record of crops sown in each season by farmers through mobile-based ground survey, that is digital crop survey. The second aspect of the scheme is Krishi Decision Support System. To integrate remote sensing data on crops, soil, weather and water resources into comprehensive geospatial system, this system is geared towards that. The mission also includes the provision of soil profile mapping and digital general crop estimation survey to provide precise yield estimates, enhancing agricultural production accuracy. This is an example of using technology such as remote sensing, data analysis and AI in the agriculture sector. The second example about the use of AgriBot is that it is a government-approved agricultural drone designed primarily for spraying pesticides and seeds. The current policy promotes its adoption by offering financial assistance to farmers through initiatives like Kisan Drone Subsidy Program under the Sub-Mission of Agricultural Mechanization. This program enables farmers to receive substantial subsidy covering a significant portion of the drone's cost based on their category. The third one is adoption of technology in disaster management. The Karnataka state government has adopted geospatial technology that is transforming disaster management by enabling data-driven decision making across all phases of it: pre-disaster, disaster response and post-disaster recovery. Key technologies like Geographic Information System, remote sensing and GPS provide real-time data collection, analysis and visualization. For example, the Disaster Early Warning System or DEWS in Karnataka integrates geospatial data with centralized broadcasting to alert vulnerable regions. Telemetric weather stations monitor rainfall, water levels and lightning, providing actionable insights into disaster preparedness. Post-disaster, the Karnataka State Disaster Management Information System uses geospatial tools to map affected areas and auto-generate reports for mitigation planning. Field data collection apps enable departments to gather and upload geo-stamped data, including damage to crops, buildings, and infrastructure, ensuring faster rehabilitation. By harnessing these technologies, Karnataka has demonstrated how geospatial innovations can improve coordination, minimize risks, and optimize resource allocation in disaster management. Let's see what are the benefits and challenges in adopting technology in land sector. Technology in general brings efficiency and ease to daily functions. This holds true for land administration as well. It promotes transparency and security in land records and management. Online platforms and mobile applications developed by government institutions encourage public participation, enabling citizens to interact with and contribute to land governance processes. However, achieving full participation requires awareness initiatives and a deep understanding of contextual, social, economic, and land-related challenges. Technology also equips the governments with tools for predictive analysis and more informed decision-making. This enables the implementation of sustainable and equitable practices. But adopting technology in land administration is not without challenges. Diverse legal, institutional, and cultural barriers exist, especially in developing countries like India. Financial and infrastructure gaps must be addressed before adopting technology-driven initiatives that have been successful in the developed world. Legal and institutional reforms may be necessary to create a framework that supports technological advancement. Additionally, the digital divide that is, the gap in access to technology, must be bridged by increasing public awareness and accessibility. This will help mitigate resistance to technological tools in land administration, ensuring smoother transition and long term benefits. In conclusion, technology holds immense potential to revolutionize land governance. By addressing challenges like cost and inclusivity, we can harness innovations to create efficient, transparent, and sustainable systems. Technology is essential for addressing modern land management challenges. Innovations like GIS, drones, AI, and blockchain are transforming land use and governance. Benefits include efficiency, transparency, and sustainability, but challenges like cost and digital divide must be addressed before that. Thank you for engaging with this session. Together, we can shape a future where technology empowers the land governance for all. Thank you.